Good afternoon, all. I would like to welcome you to the first Timber Development UK Designing in Timber webinar or talk. So the Timber Development UK is formed from the merger of the Timber Trade Federation and TRADA. This is where the Timber Trade Federation sits with your website. So head over there for lots of useful information from the Timber Trade Federation. But my main job is university engagement, which I've worked with TRADA. And if you don't know it yet, head to the TRADA site, head to the academic area and register as a student or a lecturer. That will then get you in to here with a whole load of learning resources. If you head, let me go to here. So with TRADA, with information, case studies, then you end up with a fantastic, almost 170 case studies. Everything from, the new automotive centre to a lovely little design with an egg. But why we're here today is to talk about designing timber structures. And the way you find that online is come back up here, wood information, books online, which will get you onto this page here. Click on the, what is it called, the calendar. And here we've got designing timber structures. Now, I know there's lots of either construction professionals, there's people from councils, there's architects, there's engineers, and we've got a wide range in the audience today. So although I'm talking about designing timber structures, for those of you who are interested in offsite or innovative timber construction or more about connections, and for those definitely in construction, timber frame construction is an essential to look at. But coming back to designing timber structures, just wait for my web to catch up. So here it is online. You're logged in, scroll down. If you'd like to buy the book, click on here and it'll take you to the right website. And then you can read the book all here online. But with that, I'm going to stop screen sharing and be very happy to introduce you to James and Andrew, who are going to talk about how and why they wrote the book, all about timber. And this is where it all starts. Just a cone, depending on which ones you want. And from that, you get structural timber, glulam, lay joists, and CLT. Andrew and James, the floor is yours.
Thanks very much, Tabitha. Me and James are just going to introduce ourselves first, give a tiny bit of background to how we ended up writing the book. So I'm going to start just introduce myself, and then I'm going to hand over to James. James is going to then talk to you about sort of scheme design and design of timber structures. And then I will run through a bit about the book. So I'm just going to pop this up. Hopefully. Sorry, 1 second. Okay, so my background, I mean, I've always been interested in how and why things are designed and made. And that sort of, I guess, started at university. I mean, it's been there all the time, but it sort of crystallized itself at university. I got interested in things like rammed earth. This is a rammed earth seat I made in my parents' garden. I was sort of interested, and so I wanted to try and do it. And that led ultimately to 8 weeks living and working in New Mexico, building rammed earth structures. And that sort of led then to an interest in research, and I've worked and researched a range of different construction materials. I did my PhD in timber engineering. I've worked on straw bale construction projects and done research into sort of natural finishes, natural materials. And I've also worked as a structural design engineer that's where I met James. That's where our sort of collaborations together sort of started, working on, I mean, mostly CLT buildings, but I particularly specialized in connection design, and we sort of developed a shared interest, shared passion for natural materials, timber design there. And that then led to a 3-year teaching position at the University of Bath, where I mainly taught timber design to structural engineering students, but also tutored multidisciplinary design projects. And amongst all of that, me and James also wrote this book that we're talking about today. Currently, in a move away from, I guess, both the engineering office and the teaching lecture hall, I actually work in a workshop and I design and make things with timber these days. Sort of picture on the left there is where I started. I built myself what I thought was going to be a little workshop, and I just potter around in there building things. Pretty much as soon as I finished it, I knew it was too small. So now I rent a workshop space. I work part-time there, part-time with a company called Uma Design over in Corsham, and sort of build all sorts of things, but sort of furniture installations with Uma. I've done sort of sit panels, those sorts of things. And just as an example on the right there, you can see a stair project I've done, which is sort of a wrap of an attic stair in birch ply. So I think I'm going to hand over to James now, and he's going to introduce himself.
Cheers, Andy. Right, let me just try and successfully share my screen. Okay, is that good? Can you see my slides?
Yep.
Perfect. Me and Andy, actually, we worked for the same company for a while. So we both worked for Ramboll, although in different offices. And Andy, you were based in Cambridge. I was based in Bristol, and both had experience designing buildings. My time designing buildings, I did it for about 12 years. This is probably my favorite project. It's a sixth form centre at Ralph Allen School, which is also where I went to school. So yeah, that's something that I'm really proud of. Great to have worked on something that is so close to my own heart. And as you can see, it's a timber building. It's not just clad in timber. We've got CLT and we've got rammed earth inside. I've worked on a variety of projects. So at Ramboll, I also did things like I worked on the Tate Modern extension. This is the huge piece out the back, and I particularly focused on the brick facade, which was quite an interesting project to work on. Also exhausting. I was commuting from Bath to London 3 days a week, and I mean, thinking about it now, it's crazy, but you know, kind of getting the tube where there was literally you had to lie on top of people to fit in the train and things like that, which I would not be comfortable doing now. Anyway, so I worked on projects like that. I also worked for a smaller practice called Integral Engineering Design, and worked on a variety of different projects, timber projects. I did a rammed earth wedding venue that you can see here, which also had, as you can see, a timber roof. So got to work on a variety of different projects. And thought I'd finish with this picture here, because this is kind of in many ways probably the most successful project in my career. This is Oxford Brookes University, the John Henry Brookes building. And I was project engineer on this for about 5 years, overseeing quite a large team. The project went on to win a number of awards, including being medium listed for the Sterling Prize. Pretty gutted it wasn't shortlisted, because that would have been nice on the CV, but medium listed is still not bad. And it also won a number of sustainability awards. And at the time, it was kind of very much at the cutting edge of sustainability. But what you'll see straight away, and the reason why I included this picture rather than some fancy render of it beforehand, or a nice, you know, kind of expensive paid for photograph of it afterwards, is that the project actually had a very large amount of embodied carbon, which when we were designing it, that was kind of not as anything like part of the conversation. And I'll kind of move on to that conversation in a minute. So that is kind of, at the time, this was considered at the cutting edge of sustainability, and yet it still had a very large carbon footprint. So the climate emergency, well, as I don't know if chance is the right word, but I was born in 1977, and 1977 is the year that Star Wars came out, for any of you people who follow that sort of thing. It was also the year, and I think it's hard to pinpoint exactly when this started, but it was the round about that time that people started to be aware of the impact that humankind was having on the atmosphere in terms of the release of carbon dioxide and other greenhouse gases. And so kind of at the end of the late 70s, there was conversation. People were talking about, do we need to do something? There was actually, there's a fascinating article I read. I can't remember if it was in the New Yorker or it was one of those magazines, about kind of the conversations that happened and the way people were alerted to the problem, and eventually nothing happened. Fast forward, I graduated in 2000 and I went to work for Ramboll, and kind of that's around the time that the Kyoto Protocol was agreed. Notice by then we've already passed 350 parts per million, or the 1990 level of carbon dioxide in the atmosphere. This is kind of what people kind of refer to as the level required to stay at 1.5 degrees C, roughly, you know, kind of. And I think there was a while where people were talking about going back to that. How do we get back to that, and how do we then kind of stay below that as a long-term sustainable target? Unfortunately, very little has really happened. In fact, as you can see from my little graph, really the carbon emissions, rather than going down or even stabilizing, have just gone up and up and up. In 2013, we passed 400 parts per million. And by this point, we've kind of gone from, so when I graduated in 2000, people weren't really aware of the climate emergency. Certainly in my industry, it wasn't really a conversation that was going on. I left university and did a PhD for 3 years between 2003 and 2006. And when I came back, there was much more awareness. It was suddenly a conversation that people were having. By 2010, I was teaching new units on sustainable design, looking at how we reduce carbon. But yet still not much is changing. And so 2020, that's the year that Engineers Declare happened. And people like the iStruct have started really pushing the agenda hard in terms of the climate emergency. And I'll be talking a lot more about the content that they've produced. All of that is to say that we're now in a situation where we do really need to reduce our carbon footprint significantly more than we would have done if we had started to make change in 77 when Star Wars came out, or in 2000 when I graduated. So now we're talking about needing to halve our carbon emissions by 2030 and get to zero, or by 2050. So just to kind of make you aware of just the size of the problem, and I think it's important to really understand this. Engineering projects don't happen overnight. You know, Andy's shed, which is amazing, I imagine that was designed and built in a space of a few months. But large engineering projects take years, literally years. So Oxford Brookes University, from conception to completion on site, was about 7 to 8 years. I worked on it for 5 of those 7 to 8 years. I joined after the project had started and I left before it had finished. The Tate Modern, well, that project was rumbling on for about 15 years from conception to delivery. So what's really important to note is that if we're going to halve our carbon emissions by 2030, and we're working on big projects, the time to make that change is not in 2025 or 2028. Actually, the time we need to be making that change is now. But because the projects that we start now, the projects that, you know, kind of are hitting, so in terms of the RIBA stages, stage 0, stage 1 now. So that means this is kind of the very beginning of the project where you're just thinking about what's it going to be? Do we need it? You know, where might it be? We're going to start to think about the brief, all of that sort of stuff. Those projects that are starting now, by the time we finish building them in 2030, we will need to have halved our emissions, which means that we need to be thinking about halving our emissions today. That's not a problem for further down the line. That is a problem for right now, because actually there is a huge time lag on projects. The other thing is, and we're going to talk a bit more about the difference between embodied and in-use carbon in a minute, but embodied carbon happens when we build the building. In other
I don't know if you've just frozen,
kind of over
James.
the next 5 years.
I think you just froze for a moment, James.
Am I back?
Yeah.
You are.
Great. Did you miss anything?
Maybe like 20 seconds.
I was just saying embodied carbon is kind of now, but it's not, now is in structural engineering terms means over the next 5 years. It happens over the next 5 years. Whereas the in-use carbon, that gets released during the use of the building. And actually that will carry on happening. And we tend to measure in-use carbon over the life span of a building, which is, well, we can debate that as well, but let's imagine it's 50 years because that is statistically helpful. And a lot of that in-use carbon will be released post 2050. So actually, in some senses, by the time we get to net zero, that should have all happened. We can change things in use. So we can remove gas boilers and put in electric boilers, and we can decarbonize our grid. So there are things that can happen to reduce the in-use carbon. The embodied carbon that happens now, once it's happened, we can't take it back. It's happened. So that's kind of just setting a bit of background, really. For me personally, why do I do what I do? So I left engineering industry in 2015. At the time, my kids were really upset because they were like, but Dad, you're like an engineer. That is what you do. When I kind of, that is who you are. That's your identity. And the reason I did it is because this quote sums it up for me really, really nicely. The world is not changing if you don't shoulder the burden of responsibility. Personally, for me, I wanted to do more. Changing one building at a time wasn't enough. I wanted to kind of transform not just one building at a time, but educate students and help them to change lots of buildings at a time. And now I'm hoping to go beyond that. And that's the reason why I've written lots and lots of books, which brings me to this. This is just a crazy little art magazine that I found in the Arnolfini in Bristol. But the final point it makes, it's all about sustainability, is we need to make everything easy. We need to make it easy for people to design with sustainable buildings. We need to make it accessible. We need to give people as much access to knowledge as possible, which is where the drive for producing these books has come from. The aim is not to make them hard to access. The idea is to make everything as accessible as possible. So as engineers, where is our opportunity for impact? And this is not my diagram. This is a diagram that's been around for a while. It's in things like PAS 2080. It's in things like the World Green Building Councils, bringing embodied carbon up front. And it's something that we're all hopefully aware of. And if you're not, then do go and read around it and find those publications. But basically, the simplest way we can reduce the carbon, embodied carbon in projects, is not to build. And building nothing has to become a kind of a viable alternative as we move forward. We have to be thinking about it from the beginning of a project. Now, lots of people worry that if we build nothing, that means we don't, well, what do engineers do now? But actually, engineers are required. In fact, engineers are essential to building nothing, because like people, I don't know about you, I'm 43. When I hit 40, I got a letter from the doctor to say I needed to have an annual checkup to measure things and make sure I'm doing okay. And off the back of that, then there's interventions and so on and so forth. Buildings are the same, right? So we design them with an initial design life of 50 years. Now, when they hit 50 years, that doesn't mean they're going to fall down. But it does mean that things probably have changed. Maybe the loading has changed. Maybe there's some deterioration in materials. And engineers, like doctors, need to start working with existing buildings to make sure that they're safe and make sure that we can make them durable and extend their life and all of those sorts of things. There's a whole load of opportunity for work. It's just different. It's just different to the work that we may be expecting. So the first thing we should be doing is building nothing. And we should be exploring this idea of I probably should have ordered these better. But let's stop knocking buildings down. Let's explore how we can reuse buildings as much as possible. And that's something that the AJ and the iStruct have been pushing on for a little while now. And I think it's a really important conversation. However, it's not always possible to build nothing. Sometimes we do need to build new. And so when we build new, then we need to think about how can we reduce the impact. So the way to reduce impact is to think about building clever, to think about minimizing the carbon footprint of our building and the embodied energy. And so I love this. This is Will Arnold. If you don't know Will Arnold, he works for the Institute of Structural Engineers, has been leading their kind of climate emergency information. I've got a link to that in a minute on a future slide. But Bill Gates wrote a book recently about how to avoid a climate disaster. And it turns out that building stuff is the #1 biggest thing in terms of carbon emissions, which means as engineers, we've got a huge opportunity. But Bill Gates is a tech optimist. So his solutions are all around how can we create technology to enable us to carry on doing exactly what we're doing. Will rightly points out that the easiest thing we can do is to build nothing and use less stuff. So I think it's really important to start there. Okay, so let's just quickly talk about operational versus embodied carbon. And as I mentioned earlier, so when I worked on Oxford Brookes University, we were very much concerned about operational carbon, the amount of carbon released during the lifetime of the building, and embodied carbon was a lot less of an issue. And the reason why is because at the time, operational carbon dwarfed embodied carbon. But what we're seeing now is there's been significant change in the way buildings are designed. Things like Building Regs Part L have meant that buildings have become a lot more energy efficient. And so there's a really nice study produced by Bureau Happold Engineering, which is available from the iStruct-E website. And that just shows that actually the embodied carbon in a building with a gas boiler is you know, in their study, it's just a one-off building, was about 44%, so significant. If we change that gas boiler to an electric heat pump, the embodied carbon becomes 64%. That is a big deal. So we really need to be serious about embodied carbon. So I mentioned the iStruct-E website. This is just a link to that, so you can see what I'm talking about. I really recommend just having a deep dive on that. There's loads of great information in there. So where is the embodied carbon? So it's in more than 50% is in the structure. It's in the frame, it's in the floors, it's in the foundations. So that's a big deal. That is a big deal. That's as a structural engineer, that means I am responsible for more than 50% of that embodied carbon. So if I'm responsible for more than 50% of that embodied carbon, what can I do? What can I do about it to reduce my emissions? Well, there are actually lots of strategies we can start to think about. And one of the things that they did in that study, the Bureau Happold, is they looked at 3 different materials, concrete, steel, and timber. And they looked at things like reducing specification, reducing spans, reducing material use, reducing loads, revising foundations, and making grids smaller. And what we discover is actually for all 3 materials, we can get ourselves down to below, if we really work hard, and you need a lot of opportunity here as well, but we can get below 100 kilograms of CO2 equivalent per meter squared. And that is big news. So that is what I think we should be doing. In fact, I would argue that we should be reconceptualizing the problem. We should be starting to say that actually 50 or 100, and I don't have a hard figure on what is the right number, but I think, you know, let's say 50 to 100 kilograms of CO2 per meter squared is the bare basics for the embodied carbon of a building structure. Now, what we should be doing is saying, okay, well, first of all, we need to acknowledge that that is a cost, that actually there is a cost in building, that we cannot do it in a way that there is no cost. We are going to release carbon when we build buildings. And I think we have to be honest about that. So then the question becomes, how do we minimize that cost? And what decisions are we making which is increasing the cost, and is it worth it? So when we increase loads on our building, that's going to increase the amount of embodied CO2. Is it worth it? When we increase the spans in our building, that is going to increase the amount of embodied CO2. So is it worth it? When we increase performance, when we look at things like deflection criteria, vibration criteria, we can ask the question, is it worth it? Now, there are times where absolutely, yes, it is worth it. If I'm designing a research facility that requires incredibly precise vibration performance to enable all the machinery to work, then of course it's worth it to put the additional material in to make sure that it behaves in the way it could. Although, before we do that, we should ask the question, can I locate this equipment in places where vibration isn't an issue, like maybe on the ground floor, before we jump to anything else? But there are times where it is worth it. But that should be our mindset. We should be counting the cost and thinking about the impact rather than designing without worrying about any of this stuff and then thinking about it afterwards. So why timber? Why timber in all of this? Because at the moment I've just been talking very generically about building materials generally. Well, timber does have a lower embodied carbon, and we're going to get into a whole argument about that. I know we are, and I'm going to flag up some reports and some other bits and pieces, but I believe that the easiest way to achieve the 100 kilograms or the 50 kilograms of CO2 per meter squared is by designing with timber. It is easier to do it with timber than it is with steel or concrete. Timber sequesters carbon. And again, we're just opening. I'm saying those words, and I'm aware that there's a 4-hour presentation just on that one topic, and I'm opening a whole can of worms just by even mentioning it. But I think if done right, then timber can sequester carbon, which means that we can actually use timber to draw, take the carbon out of the air and put it into buildings where it's held. And I'm actually just trying to finish an article with a chap called James Walker about how we make sure that we design timber buildings that last ideally forever. And there are examples of timber buildings that are over 1,000 years old. How do we make sure that we design them for as long as possible so that when we lock the carbon into a building, it stays there for as long as possible? Timber is renewable. It's as far as I can tell, except for straw, and I don't actually believe straw is a building material. It's an insulation material, but when you design straw bale, almost certainly you rely on other things to take the structural load, and the insulation, the straw becomes insulation predominantly. So it's really the only renewable building material that we have. It's the only material that we can keep replacing as long as it's sourced from a certified supplier. And if done properly, timber production can be circular. And we can talk about this much more detail as well, but there are certification processes like the FSC and the PEFC who can certify timber supply, and so to prove that it is coming from a renewable source. Okay, so why not timber? Because I think it's important to acknowledge that this is not a simple conversation. And I think there are a few reasons to say why not timber. First of all, timber is a finite resource. So we have timber and we have a fair amount of timber, but we don't have infinite timber. And I haven't crunched the numbers, but I'm pretty sure we don't have enough timber to replace all the concrete buildings in the world by a long shot. And the reason that concrete is so damaging in terms of CO2 is because, let's be honest, it's amazing and therefore it's cheap and therefore we use loads of it. So that's why 8% of global CO2 emissions are down to concrete, give or take. It's because it's an incredibly efficient, incredibly affordable material. Now, if we switch all of the concrete use in the world for timber use, I think we're creating a whole load of new problems for ourselves, which is why we have to start with building nothing and building less. Timber requires us to cut down trees. I don't know about you, but when I think about the climate emergency, we have to be thinking about the biodiversity emergency as well. It is not possible to cut down trees and have zero impact in terms of biodiversity. We have to acknowledge these facts. Timber takes a long time to sequester carbon. It is not a quick growing crop. We don't plant trees and a year later they're ready for felling. It takes anything from 30 to 70 years to grow timber. And therefore, it's not a quick crop to be replaced. So if we use loads of the stuff, we're not going to quickly replace it. It's going to take a long time. We need a significant plan for growing more timber to enable us to use more timber. And timber is not a perfect material. It's actually susceptible to decay. If it's not well looked after, we see problems with timber. And that's often why we end up knocking timber buildings down, because it's not been well looked after. It's not been well designed and detailed. So we need to be really careful to make sure we design timber buildings that last a very, very long time. And finally, with carbon sequestration, which effectively says the more timber you use, the more carbon you draw out of the atmosphere. We have to be really, really careful with that logic, because timber is a finite resource and therefore we can't just keep using it forever. And actually, what we need is more buildings in timber, not more timber in buildings, which is a quote from Jane Anderson. And I just love that. It's such a nice way of putting it. There is a danger to think, well, the more timber I put in my building, the better, because it will sequester more carbon. But this is not holistic thinking. That works maybe for your project, but as soon as we think about the entire timber system, that is a broken way of thinking, because actually it reduces the number of projects we can build out of timber, which is why we need to be building more buildings in timber, not more timber in buildings. Okay, so I'm aware I've been talking for a little while, but I just thought I would like to talk briefly about, where do I start? If I want to design out of timber, where should I start? And so designing out of anything is a complex process. The conceptual design process is very, very complicated. So I've said here the 23 decisions you need to make at the start of a project. And the reason it's 23 decisions, and the reason you need to make them all at once, is number one, 23 is a made up number. I don't know how many decisions you have to make at the same time. I've picked 8, which I think a structural engineer needs to think about. If you're an architect, or if you're a mechanical and electrical engineer, or if you're a landscape architect, if you're an acoustician, there are going to be a whole load of other things you want to be thinking about at the beginning of a project, which is where this number 23 comes from. There's all of these interconnecting ideas. But the thing is, once we make a decision about one of them, we make a decision about everything. And so let me just start with a simple example. The typical thing that we do is we decide what grid we want, or what column spacing we want. We say, I need my building, it's an office, it's open plan, I need a grid of at least 7 meters, because that's what an office has, which is true if you live in the UK, but actually if you live elsewhere, that isn't necessarily the case. Now that decision, whilst we might think we're making that decision in isolation, that decision actually triggers a whole load of other decisions which we may not have been aware of. So that decision might influence the material we use. So at 7 meters, timber works, but it's really at the top end of what is available and what is ideal and suitable for timber. We're going to be governed by deflection, vibration. It's going to make the amount of timber in our building significantly greater. It may well impact the cost, therefore. Whereas that is an ideal span for a concrete frame building or a steel frame building. So just that simple decision has ruled out materials. Now, if I go for 10 meters, if I say I need 10-meter grids, we are going to really struggle to make that work from timber. So I've already ruled out timber as a material before I've even started the design process. And it doesn't just have a knock on that, it has a knock on foundations, it has a knock on the type of structural system we might have. So is it going to be load bearing walls, or is it going to be framed with columns and beams? It might have a knock on whether we do on or off-site construction. It might have a knock-on effect on the type of waterproofing details and insulation details that we need. It might have a knock-on effect, well, it will definitely have a knock-on effect on the amount of embodied CO2 that we need to put into our building. So it's complicated. And so it's a little bit like a circus trick, where you kind of throw everything in the air and you grab it all at once. We may not realize that we're doing it. And that's why I wanted to flag it, because actually you might be thinking this is all very structural engineering focused. And you know, that is because I'm a structural engineer. But if you're an architect, you may be making a decision about the grids of a project before you've even appointed a structural engineer, which is changing the structural engineer's ability to come up with the lowest carbon design solution. So decisions may have already been made. You may have implicitly made all sorts of decisions without ever knowing that you've done that. A bit like this crazy circus trick. So we're kind of throwing everything in the air and it all happens at once. And that's really exciting for me. I love the conceptual design process of a building because it's really creative and there's loads going on, but it's also quite overwhelming when you're first doing it as a student or as a graduate, because there's a lot going on at once and there's a lot to worry about. And so I'm going to give you a little example and just talk through how this process might work, and also try and reassure you that it's okay and that the thing we have to do is learn. So just before I get to that, as I said earlier on, I'm really keen to tackle the climate emergency. That is why I do what I do. That is kind of what I've discovered is kind of my passion as an engineer, is to really engage in that conversation. And I think there are 3 books that will help you, which I've authored over the last few years. So the first one is the Structural Timber Elements, which is designed to help any engineer in industry make good decisions about timber design at the very, very, very beginning of the design project. I call it a pre-scheme design guide. So it's like those conversations that happen in the first 10 minutes of a project. that's when we should be thinking about this stuff, and therefore it needs to happen, you know, it's literally right at the beginning. By the time you've got the grids and the column layout and the loading and all of that stuff is sorted, by then it's too late. You've already excluded or included timber as a design solution. So if you want to be designing with timber, you need to start with that, and you need to be, that book will hopefully enable you to do that. The next one is the Conceptual Design of Buildings book, which covers steel, concrete, timber, masonry, all sorts of different materials. And what I'm trying to do there is just get engineers to think about the whole conceptual design process. And if you're an architect, I think there's plenty to enjoy in there as well. There's from systems thinking around creativity to drawing, although, you know, I know that you guys are much more practiced at drawing than certainly I am, but there's lots of fun stuff. There's, you know, stuff on communication, all sorts of content in there. But one of the things I was trying to do is engineers up till now have really put steel and concrete on this kind of pedestal of, these are my two materials that I can use. And I like to think engineers are effectively painting in monochrome. So they got light and they got dark, and that's it. That's all they've got. And what I'm trying to do here is say, actually, let's bring in the light. Let's bring in some color. Let's transform this conversation and say, actually, what about if we started thinking about timber and earth and straw and masonry and all of these different materials? Actually, let's make our palette just so much broader. Now, that doesn't mean that timber is always the right design decision, but let's start by having all of these different colors on the table and then working out which is the right one for our project, rather than just having this monochrome world. And then the final book is there, and Andy's going to talk a lot more about that, but that's just to help people on their way as they become timber engineers. Or again, if you're an architect, there's plenty in there which will be of value to you as well. So back to my 23 decisions you need to make. So I would really strongly recommend that whether you're an engineer or an architect or a quantity surveyor or whatever you do, and especially if you're a client, the first decision we should make is we should be targeting 100 kilograms of CO2. That should be our starter for 10. It has to be. If we're going to reduce our emissions to half by 2030, we have to start there. At stage 0, when we start designing the brief, one of the things we have to say is that we are committed to reducing the CO2 emissions of our project, and I think 100 is a good place to start. Now, if we start there, that then is going to lead us to making some decisions. Now, as I said, you don't have to build with with timber to make that happen, but I think it's a lot easier to start with timber. So, for example, that might push us towards thinking about cross-laminated timber as a solution, which might give us target spans of 5 meters. You can go up to 7 or 8 meters for CLT, but remember what I said earlier about trying to minimize the amount of material in our project. We kind of get diminishing returns. As the spans go up, we have to use a lot more timber to increase the span. So a 5 meter span will give you a really, kind of really efficient design, well-considered timber floor, which means our structural layouts, our column grids, and all of that sort of stuff will be on 5 meter centers. Now, if we're using CLT, that potentially pushes us towards a load bearing solution. So what I mean by that is, rather than having columns and then beams and then slabs on beams, we'll have structural walls and then we'll span between those walls. Now, there's lots of reasons why you wouldn't do that. So one of the things I'm thinking about at the moment is future flexibility. And the downside of load-bearing walls is it does make it harder to change the way we use spaces later on. So we might say, well, actually, I don't want to go for load-bearing. I do want to go for either a hybrid system where we have a mixture of load-bearing walls and then beams and columns, or I want to go for a frame system where the whole building is made from beams and columns, with the exception of the stability systems, which are going to be made from, that could be bracing or that could be walls. But let's just say for argument's sake, that pushes us towards load bearing. Now, load bearing, one of the big places where there's embodied carbon is not just in the superstructure, it's down in the ground, it's in the foundations. And the nice thing about load bearing structures is it means that the load intensity on the foundations is much lower, because we're now spreading the load out along the length of a wall rather than concentrating all of that load down onto one point on a column. And then therefore, that means that by going for that reduced load, we can go for strips, and we might even get to a point where we can have concrete-free foundations. And timber is light, so timber is reducing the load, we're spreading the load. So all of these things enable us to think creatively about the solution type of foundation type we have. And as I say, possibly go for concrete-free foundations. And it also opens up the opportunity for prefabrication, which means a lot less waste, and we can optimize the usage of our material. And it means that we're probably going to design for the insulation envelope to be outside of the timber. So we're going to kind of wrap the timber to try and keep the timber dry and warm, which is going to hopefully deal with its durability issues. So that was one example of how we might think through that process, and how by starting with the targeting 100 kilograms of CO2 per meter squared, we can actually use that as a launch pad to then think about all of the different design decisions we make right at the beginning of a project to try and come up with as sustainable a solution as possible. There was a recent article, and I just wanted to talk about this very briefly, that comes at this from a very different line. Now, this article has created more debate in engineering circles than I can remember for a long time. I've seen people lose their temper over this, which is exciting because, you know, engineers are like Ents. I don't know if anyone knows about Ents in Lord of the Rings, but, you know, I think it takes a lot to get an engineer really passionate and excited and kind of really kind of sharing all of that emotion. But this has done it. And this article is about the fact that effectively timber, concrete, steel, they kind of have the same embodied carbon. Now, I would argue that the outcome is not wrong, but the wrong question was asked. Because the question that was asked, it was a 9 meter long beam. Now, a beam that's 9 meters long, I can tell you straight away that timber is not going to be the right material for that design problem. It's going to have all sorts of things that you would want to consider. And this is where, you know, if you start with the wrong question, if you start with the wrong assumptions, you're not going to end up in the right place, you know. So actually, whilst this article and this is kind of the where it goes, you know, the Concrete Association then sent out a newsletter. There is currently no single structural material that can be considered lowest carbon as a rule of thumb across projects, which is based on that article. You can understand why engineers are getting exercised about this. And the whole point is they started in the wrong place. So we have to start in the right place. We have to start by thinking about lowest carbon rather than starting anywhere else. And then that drives all the other decisions. So if we do that, hopefully we will end up halving our emissions. That is the long term. That is the goal. That is the plan, is to get to half emissions by 2030. And then from there on in, you know, trying to get them down to zero beyond. So just a reminder, and this is in red because it's kind of a warning, you can start anywhere and it impacts everything. So if you are starting a project and the first thing you're thinking about is the grids, or the first thing you're thinking about is your structural system, or the first thing you're thinking about is I don't know, the envelope, or wherever it is you start, that's going to have impacts on everything else. Okay, but you don't need to panic. Stay calm. There are lots of different solutions. Try some and see what works. And we have to learn. We have to be reflective. We have to share information. We have to work together. We have to learn from our mistakes, and mistakes are going to be made across all the different materials, you know, not just in timber, but in steel and in concrete. We're going to have to learn, and we're going to have to continuously commit to doing better. And so I believe that is my last slide. And so I'm going to hand over to Andy, who hopefully is going to take over and talk a bit more about the book. And Andy, I'm so sorry. I had no idea that I spoke for so long.
That's all right, no problem.
I'm so sorry.
Thanks very much. I think that was really useful context to what I'm going to talk about with the book. I want to, I want to give an overview of where the book came from, why it is the way it is, what we put into it. And I'll also declare at this point that neither me or James get any royalties or anything from the book. I'm not promoting it in that sort of sense. I'm promoting it as a bit of work that I've contributed to and think will be very valuable for lots of people. So let's have a look through. So, I mean, James touched on why timber. I mean, for me, I suppose, why did I end up writing a timber book, a book on how to design with timber? It's partly because that's my background, my experience. But me and James also have discussed and written an article previously about the idea of timber being a really interesting material to embed within education. It's a very accessible material. You can get hands-on with it. You can build things. You can nail stuff together. You can screw stuff together. You can buy it in the shop. And so I do think, from an educational point of view, a book which focuses on structural design around timber is quite valuable because it can link in across a broad spectrum of education. So just briefly, I suppose, how did the book come about? I mean, it's born out of a shared interest and experience of designing with timber and teaching. And we were really keen to use our experience in teaching timber design to create a resource, essentially, that would sort of give students and anyone in industry, or anyone with anyone with a sort of strong interest in timber design, to really get to grips with it beyond just sort of a dry book on sort of structural calculations, or an architectural book which has lots of photos but not much technical information. So we wanted to create an accessible and sort of friendly book about timber design. I think also we're big fans and advocates of drawing, and we've used that a lot in our teaching, and we wanted to get that into a book as well. And ultimately it came about over 2 years of work on and off, which, you know, when James asked me if I wanted to contribute to a book, I thought, yeah, that'd be fine. I didn't still sort of imagine to be writing it 2 years later, having had a child in between starting and finishing it. But you know, these things take time. Good things come to those who wait, don't they? So why did the book come about? I mean, we felt there was a real need for an approachable book about the design of timber structures, one which didn't really have, well, it was accessible, essentially. It was readable, and you could digest the information both visually and through reading the content. And we wanted to provide something that had a breadth of content suitable for teaching and self-learning. There was definitely a sense from both sides that we'd created sort of notes and things for our students that we felt could be more formalized or sort of structured in a book, and that we could both bring elements to that. And well, personally, I think we really wanted to include things in that book that might seem obvious to people who have worked with timber, who have experience as working as a design engineer or as an experienced architect, but often students or people who are starting out don't necessarily know. And it's interesting when you start teaching, you see the gaps in knowledge, you experience the gaps in knowledge that you didn't expect to see. So for example, I've taught half a timber course, including connection design before, and then towards the end of a lecture, halfway through, I've had a student ask, you know, what's the difference between a dowel and a bolt? And it's just assumed knowledge. And it's a slightly embarrassing question to ask potentially, but if you don't ask those questions and you just march on and pretend you know, then that can have all sorts of disastrous implications. So we really wanted the book to really address, you know, a broad range of things, but to not be pretentious in any way. It's meant to be accessible. And the book, one of the really good things I think about the book is it offers lots of pictures. So I was flicking through it the other day preparing for this, and pretty much every single image in there is either a photo or it's been hand drawn by myself or James. And we really, well, we sort of, it was a key requisite for writing the book was that we could hand draw things, because I mean, personally, I think hand drawn images convey much more information than either a computer graphic or text. So, I mean, just as an example, this is an excerpt on the left from Eurocode 5, which is the only information you really get about something called the rope effect, which is where bolted connections are dragged through a connection. It's a dry bit of text and it doesn't really explain what it is, whereas in the book we've been able to include, a graphic which actually shows how the timber is crushed, what you're calculating when you're calculating the capacity of a connection like that. And we've also tried to explain some what would be considered maybe tricky concepts, so stability being one of those. And I've stolen this quote from James, so if anyone wants to know the source, they'll have to ask James, but I felt quite flattered when I came across it in the resources we were sharing in preparing this, and I'm really pleased that people have used this book and found it readable for things like stability. And we have tried to include in the book sort of analogies to help explain concepts. So for example, how a timber wall panel might be designed. You do sort of, it's analogous to a big bit of rubber with a sort of bit of plywood on top, and it's joined with Velcro, and so you get sliding and sort of tearing of that Velcro in the same way that you would get deformation of screws or nails. So we've tried to make things clear as possible. As well in the book, all the worked examples are handwritten and illustrated by myself and James, and it was a big bit of work, I guess, actually doing that, because it takes quite a long time. But I think it's really valuable. I mean, we're not saying that this is the only or best way to present calculations, and if you use design software, then they give out really clear printouts of the actual calculation they've done, but they don't give you an introduction, they don't give you necessarily a design context or a design overview. And so we wanted to provide examples of how design calculations can be clearly presented, particularly by hand. And I do think there's a value in producing hand calculations, both in terms of sort of efficiency and really getting your head into how something is working. So what does the book cover? I mean, it's kind of tricky to explain a sort of several hundred-page book in 10-15 minutes, but I want to give a bit of an insight into some of the areas that the book covers and why. So the first chapter is, as many timber books are, is dedicated to sort of what timber is, what we have to consider from a design point of view, movement, things like that. But in particular, a section that I like and think is really valuable is a section on sort of timber species. So we sort of discuss some of the primary species that are used, certainly in the UK and across Europe, for timber structures. So one of those would be thick spruce or potentially oak, and this photo here is a big pile of Douglas fir. And I think that's really valuable information as a designer, because it can make a building special, I think, or more special when you start getting into what species you're going to use. That's when you know you've really sort of got into timber design, is when you're thinking not only, oh, is it timber, but is it Douglas fir, is it spruce, is it oak, is it sweet chestnut? And I think those things also touch upon some of the sustainability issues that James mentioned, in terms of, timber's not a renewable resource, but if you're in the southeast of England, you might be able to get glulam sweet chestnut from coppice woodland, and that is renewable. That's cyclic, that's part of the maintenance of those stands. So we discuss different timber species, and I think as an example of that, this is one of my sort of favorite local timber buildings. This is the entrance building at Westonbirt Arboretum, and the frame for that is made from sawn Douglas fir timber, air dried, locally sourced. And I think that makes that building really special for me. It's not just a timber building, it's a timber building that has specifically been designed for a specific, or with a specific type of timber, with minimal processing. If that was glulam, the embodied carbon of that would be much higher, and it would be less interesting to me, at least. So in the book, we've tried to sort of structure it in an order of almost, I guess, yeah, sort of embodied carbon to some extent, not by design, but it starts focusing on very simple sawn timber element design. So how do you design a timber joist? You scale it up, it's a timber beam, or a timber stud, you scale that up, it's a timber column. And then we move into how you design with glulam, and then from there, cross-laminated timber. And I think it's really important to, I think it's really important to place value on those early chapters and starting with minimal processed timber sometimes in design. I think cross-laminated timber is an amazing material and you can do amazing things with it, but it is not by any means a sort of panacea to all our problems. It's a very hungry material for volume of timber, but it has a place. And I think from a design point of view, there is a gap in knowledge there. And so I do think the chapter that James predominantly wrote on cross-laminated timber design is really valuable. It really demystifies what is a little bit of an unusual material from a design point of view. And the book, we also discuss sustainability, and I know James has sort of touched upon this and the complexity of it, and also about biodiversity. I mean, this is a photo from, is it Austria or Germany? It's on the border somewhere, Europe, Central Europe. But this is all spruce, and this is 50,000 cubic meters of solid spruce tree trunk, and that is a 12-day supply for this sawmill. And so it gives a sense of scale of, you know, even where we're at, we're not using timber that much, certainly in this country, for our buildings, and this is already the sort of scale of production. It's a phenomenal amount of trees. It's mind-blowing, and it does make you sort of think like, wow, if we want to scale this up, it's quite incredible. And I think also from a biodiversity point of view, I mean, you go to Europe, it's just spruce, 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 spruce. Everything is spruce. So, you know, God forbid we ever get any sort of spruce beetle or something. But, you know, I do think there's some interesting discussions on sustainability, and we do sort of touch upon those in the book. And I think, again, one of the valuable things the book covers, from my perspective at least, as a former sort of lecturer of timber engineering, is it covers both sides of the story. So it covers both how you calculate the load on something and the strength of something. I think there are a lot of books and a lot of lectures out there where you get taught how to design the strength of a timber beam or a timber column, and that's great. But if you don't actually know how to calculate the load going onto that beam or column, it's kind of useless, because I don't know, anyone who's sort of taught in a university or whatever, then you may well have marked a piece of work where the method for sizing a beam is perfect, but the beam has come out as, you know, 50 mil by 20 mil because the load is minimal, or the opposite, it's a meter deep. So we have tried to, specifically for timber buildings, explain how you can calculate the loads on elements, because it's a really important part of the design process. And we've also included a whole chapter on sort of practical design considerations, so particularly around connection design and detailing, both from a sort of buildability point of view, a durability point of view, and an aesthetic point of view. And I think this is something, certainly having now made a few timber sort of built-in furniture elements and built-in elements, the importance of connection design and how you get something together is hard to emphasize enough. almost needs to be there at the start. I mean, everything needs to be at the start. That's the problem. You talk to anyone about anything, they say, oh, my bit should be at the start. But I do think this is a really valuable part of the book in terms of practical detailing of timber structures. So for example, in this picture, you can see the difference of a flitch plate connection. You can either sort of drop a beam on, leave it hovering in space, try to drive dowels through, or you can notch the top of it and you've got a locating dowel. It's suddenly much easier and much quicker. And there's also content on design considerations for assessing and repairing existing buildings. And again, I think in the context of what James talked about, this is really important. There are a lot of timber buildings out there, and I mean, there's also a huge amount of domestic or commercial buildings with timber roofs. They're not necessarily timber structures, but they have timber roof structures, and being able to repair and assess those is really important. And I think, to be honest, it's going to become more important because at some point, 30, 40 years, some of us are going to need to be experts in assessing and repairing CLT buildings and those sorts of things. So I think that's an area which is very interesting personally. And so in terms of finding out more about the book, we sort of, I hope that you can, when you flick through it, or when you read it, it will help you feel confident about approaching timber design. That's the genuine hope and expectation of writing it. Personally, I would have loved to have had this book around 10 years ago when I was learning timber design and going into industry. It would have been really, really valuable. But it doesn't cover everything. It can't, you know. It gives you a good solid foundation. So we've included as a chapter at the end a sort of quite comprehensive list of other resources that you can use. And I know Tabitha has managed to get an additional discount for anyone who does want to buy the book, which you can get from the Trada website using this code DTS10. And if you're a lecturer, then you can apply for a copy, an inspection copy, which you can use to look through. And I think you can read excerpts as well on the Trada website. So, I mean, I know that's a bit of a whistle-stop tour in the 15 minutes, but I do hope it's given you a little insight into the book and the sort of content that we've included in there. So